A very good morning, dear students. In this video, we are going to learn about this finite word length effect called input quantization error. Let's solve a problem in this topic. For the recursive filter shown in the figure, the input x of n has a peak value of 10 volts represented by 6 bits. Compute the variance of the output due to AD conversion, that is analog to digital conversion. And this is the filter diagram that has been shown here. Okay. Now let's write the given values first. It's mentioned that the given signal x of n has a range of 10 volts. So R is 10. R value should be taken as 10. The next is, it is represented by 6 bits. The number of bits including the sign bits is 6. Okay. Now we have to compute the variance of the output, that is steady state output noise power due to this analog to digital conversion. And this steady state output noise power is represented as sigma E naught square. This is how it will be represented, sigma E naught square. And if you look into the formula for sigma E naught square, whenever we want to calculate the variance of noise at the output, first we have to calculate the variance of noise at the input. That is, input steady state noise power has to be calculated. And this steady state input noise power is given by sigma E square, for which the formula is Q square by 12. Okay. So the variance of the error signal at the input is sigma E square. This is what we have to find first. The formula for finding the sigma E square, that is, this is input variance, steady state noise power at the input. Okay, Q square by 12. Q is called the quantization step size, and this quantization step size is given by the formula R by 2 power B, where R is the range of the signal and 2 power B is the number of quantization levels. And it is given in the problem that the range of this signal is 10 volts and B is 6 bits. By substituting these two values of 10 and 2, B as 6, we are getting the value of Q as 0.15625. Next, as per this formula, input signal, that is input variance or input steady state noise power, is given by Q square by 12. So it is 0.15625 square by 12. And the answer for which is 2.0345 into 10 power minus 3. So we have calculated the input noise power. Next, we are supposed to find the output noise power. The output noise power is given by the formula sigma E naught square is equal to sigma E square, which is nothing but the input noise power. This is the input noise power multiplied by summation I is equal to 1 to n residue of, we are going to solve this with the help of residue theorem. Actually, the formula has contour of integration, and this integration can be simplified with the help of this residue theorem, for which the formula is summation I is equal to 1 to n residue of h of z into h of z inverse into z inverse at z is equal to pi. And here, while finding the residue, we usually will consider only the poles that lies inside the unit circle because of this contour integration. Okay. Now, in the given problem, we don't have this h of z directly. H of z is not mentioned directly, but it is, the system is represented as a signal flow graph. Now, from this signal flow graph, we can represent the output and input relations. So here, as per this diagram, this y of n is nothing but x of n plus 0.93 into y of n minus 1. In the feedback path, we have 0.93 y of n minus 1. So this 0.93 y of n minus 1 and this x of n added together. Here we have an adder. So these two gets added together to get the to obtain the output y of n. So it can be represented as a difference equation in this form. Y of n is x of n plus 0.93 y of n minus 1. Finding z transform on both sides, this is going to be y of z, and x of n's z transform is x of z. For y of n minus 1, it is 0.93 z power minus 1 y of z. Bringing this y of z term to the other side, it's going to be y of z into 1 minus 0.93 z inverse is equal to x of z. Finding h of z, which is y of z by x of z, it is nothing but 1 by 1 minus 0.93 z power minus 1. Now h of z, the same h of z can be expressed using this positive powers of z as z by z minus 0.93. The same h of z, if you take z inverse outside and simplify it, we are going to get it as z by z minus 0.93. Now this is our h of z. And in the formula, we have residue of h of z inverse into z power minus 1. We have h of z now. We have to find what is h of z power minus 1. And this can be obtained by replacing z as z power minus 1. So z power minus 1 by z power minus 1 minus 0.93. Now multiply this h of z with h of z inverse. And finally, this two terms, the product of these two terms has to be multiplied with z power minus 1. So the entire resultant product of this term, h of z inverse into z power minus 1 is represented here, which is z by z minus 0.93 into z inverse by z inverse minus 0.93 into z power minus 1. Now if we simplify this z and z inverse gets cancelled. And in the numerator, we are left with only this z power minus 1 term. So it becomes z power minus 1 by z minus 0.93 and z power minus 1 minus 0.93. Now we have, if we analyze this, we have two poles, and those two poles are z is equal to 0.93 and the second pole is z is equal to 1 by 0.93. It is 1 by 0.93. So if we analyze these two, only this pole lies inside the unit circle. Whereas if we consider the second pole, the value of which will be greater than 1, so this pole will not lie within the unit circle. So while calculating the residue, we have to consider only the pole that lies inside the unit circle. So it is enough to find the residue of only one pole, which is z is equal to 0.93. We can neglect this second pole. No need to find the residue for this particular pole. So how to find the residue of this h of z inverse at z is equal to 0.93? With this product of h of z inverse into z power minus 1, we have to multiply z minus 0.93. Whenever we substitute z is equal to 0.93, this has to be multiplied with z minus 0.93. So after multiplying this product with z minus 0.93, we can cancel these two terms. So we are left with z power minus 1 by z power minus 1 minus 0.93. And here we have to substitute z as 0.93 and find the simplified result. So if we substitute z is equal to 0.93 and find the simplified result, we are going to, that is, instead of z, it is 0.93. Here also it is 0.93. After simplification, we are getting the answer to be 7.4019. Now this is the value of the residue that we have calculated. As per the formula for finding the output round of noise power, we have to multiply this residue term with this input signal noise power. So this 7.4019 should be multiplied with sigma e square, which we have determined in the first step, very first step. Sigma e square, we have determined it as 2.0345 into 10 power minus 3. So this has to be multiplied with 7.4019 to get the total steady state output noise power, or you can say variance of the output at due to AD conversion process, and its value is 0.0151. So this is how you have to solve all problems related to the input quantization error of finite word length effects. Hope you have understood this. Thank you.